Good evening, sweet people, or good morning, or good afternoon. Just want you to know that I love you dearly. I hope that all of you are doing well, and I don't want to talk about how many times I've recorded this video, deleted it, and recorded it again. So I'm going to give this another try. Unfortunately, it is on Riemann sums, which is a struggle for all of you. In other words, you might remember that name, but might not necessarily remember the concept. So I'm here to help you remember a few things. Riemann sums were the beginning of integration. In other words, we talked about left and right rectangular approximation method. What that looked like was basically if you knew an interval from A to B, then what we decided is you could take an infinite number of rectangles and determine an approximation for that area. As a matter of fact, we used the limit as n is approaching infinity. But before we got that advanced, and there is a little bit of a lag in between the computer and the iPad. Sorry about that. But before we got there, we actually were given a specific number of rectangles. And n equaled the number of rectangles, okay? So all of that being said, we're going to look at two more Riemann sums, okay? One today and one tomorrow. Today's Riemann sum is going to be for trapezoids. First and foremost, I feel the need to remind you of what a trapezoid even is. A trapezoid can look like this specifically. And what we're going to do is we're going to take a trapezoid and we're going to turn it, rotate it 90 degrees counterclockwise. And when I do, it's going to give me the shape. Okay, that's a very important shape for this graph especially, because if I look at this, this is going to give me a much better approximation method than what just a rectangle would. And then it's the same idea for Riemann sum. I'm going to add the sum of each area of a trapezoid together in order to get the overall area. Now, we will not be using a limit as n is approaching infinity because we learned soon the shorthand rule, where you're adding 1 to the exponent and dividing by a value, and the fundamental theorem of calculus, okay? So what we are going to do, though, is focus. If they tell me a specific number of trapezoids, how do I determine that? Well, the first thing that you need to remember is how to solve for the area of a trapezoid anyway. And that formula is 1/2 times the height times base 1 plus base 2. We're going to take a few minutes and remind ourselves what that exactly looks like, okay? When you see the trapezoid rule, without knowing any of that information, you can kind of put some of this together because you get the 1/2, very similar, because this is the area under the curve using trapezoids. So 1/2 is still true. The next thing is the height. Well, the height in this case is actually going to represent that bottom length. That height is also known as delta x. Delta x can be calculated by b minus a over n, okay? So I'm going to plug in b minus a over n for that value. And then you have all of this weird stuff in the middle. If you've already written down the trapezoidal rule, you've seen that it looks kind of odd, but let's talk about the reasoning behind it. Each of these trapezoids have two bases. The difference is that some of these bases are overlapping and some are not. So if I look in yellow here, these are all the bases that are overlapping. The two ones on the exterior are not. So this one is actually known as the height, f of x, subscript 0, and this one, f of x, subscript n. Everything else is being used multiple times. So you have all of this times, and you start out with f of x, subscript 0, then you change to plus 2, f of x subscript 1, blah, 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 all the way up to the second to last number. And we're just going to call that n minus 1. And then I add on that very last term, which is f of x of n. And that, essentially, is my trapezoidal rule. That's why all of the inside terms that you see here in yellow are preceded by a 2. Okay, so variables. Let's talk about those. First off, a and b are just over the variable, the integral from a to b, or interval from a to b. Same thing. Okay, nothing's new there. My f of x is always given to me right in front of the dx. It's some type of function. It could be x cubed. It could be sine x. It could be x plus 3. It's some type of function, and we have to figure that out. For trapezoidal rule, they will specifically tell you the number of trapezoids that you'll be using. And most of the time, that ends up being a number like 4 or 8. It's a very pretty number. All right, h. Let's talk about h again because I need to know what that height is, and that's coming from this b minus a over n, okay? Where I would say, all right, well, I know what my b is, and I know what the a is, and I know my n, and I can calculate that. The last thing that you have to actually pay attention to is the inside values. All of those numbers, there's a little trick to it. All of those numbers that you see, it's listed out individually. But the way that you figure out what they are is they are separated by b minus a over n. And I'll explain what that means in just a minute. And it's always one more term than the number of trapezoids that you use, not rectangles. It's always one more. This will make a little more sense when we're working our first example. Okay, so let's work it. And once again, a lag in the screen. Okay, so use the trapezoidal rule to approximate the integral from 0 to pi of sine x dx and solve for n equals 4, period there, and erase that period there. It would be silly to end that sentence up there. Okay, so let's look at what we know. We know some of this information. I'm kind of getting ready for the trapezoidal rule. I have it kind of written out. A is going to equal 0. B is going to equal pi. It tells me that n equals 4, so I'm set. It's asking, okay, sine x. Yep, we're going all the way. We're starting out with trigonometry. So I kind of have everything that I need. I'm set to know what 1/2 is. That's easy. B minus a over n. I can figure that out. But now I have all of this information here. I know that the first one is just one number. And the last one is just one number. It's being multiplied by 1. But how many terms do I have? Well, it's telling me n equals 4. Because it says n equals 4, I know that I'm going to need 5 terms. Okay? So 2, 3, 4, 5. Okay? All of these terms on the inside are going to be multiplied by a 2. For reasons that we talked about just a few minutes ago. How do I figure out what these terms are? Well, there's a cheat rule. The first one is actually going to be the value of a. Now, that doesn't mean I put 0 in here, and that doesn't mean I put pi in at the end. But I'm going to use f of x subscript 0 and f of x subscript, in this case, 4, because I have a total of 5 terms. N is 4. You can go back and make those comparisons. But when I'm trying to figure this out, this is actually going to be sine of 0 and sine of pi. So you plug in your a and your b value. Okay, now let's clean this up a little bit because it's getting a little crazy and we don't need that. So the integral from 0 to pi of sine x dx is 1/2. So that's normal, that's good. 1/2 is not anything unusual. B minus a over n. We're going to take some time and kind of identify that would be pi minus 0 over 4. Okay, B is pi, A is 0, 4 trapezoids. Then I'm going to multiply that by, well, now I have to have the official f of x sub 0. That means I have to use my function. My function is sine x. I'm going to start with sine 0. And based on what we just said, we're going to end with sine pi. But how do I figure out all of those numbers in between? I might know that they're all going to be multiplied by a 2, but what does it mean as far as like what is the rest of that number? What is the rest of this one? What is the rest of this? Well, I know I have 5 terms because I have 4 trapezoids. In order to figure that out, I've got to come back to my b minus a over n. b minus a over n is pi over 4. That tells me how far apart each one is. So I start at part A, and if I have sine of 0, I add pi over 4 to that to get to the next one. So 0 plus pi over 4 is sine pi over 4. I know that you don't like that. Don't make this too complicated. You add pi over 4 to that again. Some of you are like, how do you even do that? Pi over 4 plus pi over 4, that means you have 2 of them. And then you reduce. Okay, so don't forget the math that you do know. Sine of pi over 2. Okay, and then I add pi over 4 again. Okay, some of you are like, yeah, but you're doing crazy math right now. This is just like adding fractions. I know that you might not like that, but you should remember that. 2/4 plus 1/4 is 3/4. So I just throw the pi on. So this would be sine of 3 pi over 4. And this is the beautiful thing about math. You can use yourself and actually check it here. If I add pi over 4 again, that gives me 4 pi over 4, which is pi. Okay? All right, so hopefully that helped you out a little bit. Now to actually solve this problem. So I have the integral from 0 to pi of sine x dx equals, this ends up simplifying to be 1/2 times pi over 4. Okay, now for the trig, sine of 0 is 0. Yes, you do need to know that. No, you should not put that in your calculator. Sean Tyler. Plus 2 times the sine of pi over 4, radical 2 over 2. Plus 2 times the sine of pi over 2. Plus 2 times the sine of 3 pi over 4. Oh, I forgot a plus sign there. Plus the sine of pi, which is another 0. Now, if this wasn't a value that you recognized, if this was 2 times the sine of pi over 12, then you would put it in your calculator. But if it's something that's like pi over 4, pi over 3, pi over 6, and you should recognize it, you're probably going to have to figure that out without your calculator. So 2's cancel, these 2's cancel. When I clean this up, I end up with pi over 8 times 0 plus radical 2 plus 2 plus radical 2 plus 0. Of course, the plus zeros are kind of irrelevant at this point because adding nothing to that. When I do combine like terms, radical 2 plus radical 2, if I add 2 of them together, I just have 2 radical 2. Then I bring down my plus 2, and I'm multiplying this by pi over 8. Hopefully you can see that you can factor out a 2, cancel, and this would leave you with radical 2 plus 1 all times pi all over 4. And that is your answer for the trapezoidal problem. If you guys have questions, I will take time to explain it to you on Zoom on Wednesday.